add a couple of things before we start, and we need to follow the schedule. And I would like to say once upon a time, but a while ago when I was a graduate student, there was direct or indirect liquefaction. Today we have new fancy names: CTL, GTL, BTL, X2L, everything to liquids. So I think the concept is the same, and I'm very glad that we attract this much crowd. And I would like to introduce the first speaker, coming from Witwatersrand University, and the presenter is Wazi Kubelwana.
No, me.
Yes.
David Glaser.
I'm sorry.
No, they got it wrong in the program.
Thank you.
Right. How do I get to my talk?
I assume that it's sorry.
I'll put it on the computer.
Yes.
No, that's my student. All right, thank you very much for listening to me so far. We were looking at a new route to FT synthesis, and in doing that, we wanted to look at the gasifier to try and get the products we want. And various reactions occur, some are desirable or not, but we like graphical techniques, and we like to understand things in terms of graphs. So I'm going to just give you a very simple talk using mass energy balances together with reaction equilibrium. So the current process for syngas uses carbon monoxide and hydrogen in a 1:2 ratio, and I'm all wired up now. Okay. Thank you. That's a minute of my time. So the normal process is to get rid of the CO2, and we're saying maybe that's not necessarily a good idea. And if you go the full other way, you can use CO2 plus hydrogen in the 1:3 ratio. And we believe, for reasons which I'm not going to go into this talk, that will reduce CO2 emissions in the end. So, we call this the CO2 route, and we need to know whether a gasifier could in principle produce a syngas, and that should be CO2, hydrogen, in the 1:3 ratio. Amazing how you only see the mistakes now, not when you're doing it. So, just to give you an idea of why we're doing this, if you look at tons of CO2 emitted per ton of hydrocarbon produced, and you look at the ultimate target for the current chemistry, you get a number of about 3.75. And if you go to this new chemistry, which we've done, and again, the methods of getting the targets are not our talk today. There are some talks later on which will explain some of this. You can actually reduce the CO2 emissions in principle by ton per ton of hydrocarbon produced. So that's why we're trying to go this way. So if you look at the reactions in the gasifier, then the first one is carbon plus oxygen, but that essentially goes to completion. So that's not a big issue. The other one is carbon plus water goes to CO and hydrogen, and let's for the moment call that extent of reaction 1. That's the carbon going to plus water. And we've got the other one, which is the water gas shift reaction, and that's CO plus water going to CO2 plus hydrogen, and we call that extent of reaction 2. And then the question is, if we do a plot of extent of reaction 2 versus extent of reaction 1, what are possible products from the gasifier? We've drawn some funny lines there and asked, is that a possible gasifier route that one could have get? So we're going to use this doing only material energy and reaction equilibrium, material energy balances and reaction equilibrium. So let's consider all the species in turn. If we look at NCO, the number of moles of NCO, it's the extent of 1 minus extent of 2, and obviously CO must be greater than or equal to 0, so we can put that greater than equal to 0. And if we now plot that on that diagram, you get a straight line like that. And the moles of CO below this are positive, and this line is fixed. There's no, you can't move that line because that, if you looked at that equation, unless you fed CO in your feed, you can't move that. We can now do the same for all the other species. NCO2 is NO2 plus E2 greater than equal to 0. Notice in this case the intercept does depend on the feed. The number of moles of oxygen we feed. The number of moles of water depend on the number of moles of water we fed, minus E1 minus E2 greater than 0. And again the intercept is fixed by the amount of water we feed. But the slope, notice, is fixed. And the hydrogen, the same. Doesn't matter the amount that we feed, there's nothing fed, so there's a fixed line and of a fixed slope. So if we now put this on a plot, what we get is the following. That this area here between NCO2 equals 0 in hydrogen, in CO equals 0, in water equals 0, for a particular value of water obviously, and for a particular value of, it was only water I think, that is the feasible region. So now we've got some idea of what is possible. However, if we increase the water, we can change that line, not the slope, but that line. So we can increase the feasible region by increasing the water. I haven't said whether that's desirable or not, I've merely said that is possible. If we increase the amount of oxygen fed to the gasifier, we get the same result. We can increase the feasible region, again down here, and again I haven't said whether that's desirable or not, but that's the feasible region we can attain. So, the energy balance is a similar straight line on that diagram, because if we write the energy balance in terms of assuming that we've got feed at room temperature and feed and products at room temperature to start with, we can use delta H as a formation. We can make it more fancy afterwards, but in the beginning that's good enough. So the energy balance is also the airlines are still trying to get me my baggage, so I don't have anything suitable to lecturing. The energy balance also corresponds to a line on this diagram. And the intercept depends on the amount of oxygen that we fed to the reactor, because the oxygen here appears as the amount that we need to combust. So the slope of the energy line is fixed, but the intercept depends on the amount of oxygen we feed. So again, we can look at that, and for different amounts of oxygen, we can do that. Now, notice that what we would like to do is to have a system where all the energy we produce is stored in the chemicals. We don't want to have excess energy produced in the system. We don't want to throw energy away. So we're looking for an opportunity to try, whoops, wrong. We're looking for an opportunity to get the value of the energy balance equal to 0. because that means we've effectively stored all our energy in the product. And the more energy the gasifier loses, essentially it loses it to the product gases. So now what we can do is see that the energy balance for Q equals naught, that is the heat losses, cut off this region of the feasible region. In this region here, we would have to add heat. We're adding heat by putting in oxygen, so why would we want to add heat in another way? So what we've done now is cut off that region because of the energy balance. So this blue region now remains our feasible region. So also, we note that this is Q equals naught. If we operated here, we would reject a lot of energy. And that wouldn't be what we were trying to do, because we want to store as much of our energy in our chemical product as possible. So, the closer the gasifier operates to this line, the more of the potential energy is stored chemically in the syngas. Now, let's look at hydrogen to CO ratios. If we have a hydrogen to CO ratio, we get 1.5 here. If we have a hydrogen to CO ratio of 2, you notice that what stops us going further is different. This is determined by the energy balance, but this one isn't determined by the energy balance, it's determined by the water equals naught. So what we can do is, if we want to get a higher extent of reaction 1, we can add more water to the feed. So this is already giving us very useful information. It tells us add more water to the feed, and then we'll be able to reach that point where the energy balance will suddenly become limited. But of course, we don't want to add vast quantities of extra water, because we'll end there anyway, so it tells us how much water we should add. Also, if we would like to get a hydrogen CO2 ratio 3, as I spoke about earlier, then this is the line. But if I wanted to get 1.5, and I haven't said what I wanted to get yet, you can see that again I'm limited by the water consumption. So I can reach this point here by increasing the water consumption. So what it's saying is that we can get better by increasing the water consumption. Notice here, notice here we're limited by the energy balance if we want to go to hydrogen 3. Here, in order to go up to here, we would need to put more energy. What about water-gas shift equilibrium? Well, we can draw lines of water-gas shift equilibrium on this diagram. And here you can see it for 700 K, and here you can see it for 1200 K. So decreasing the temperature will lead to less CO production, and there's a mistake. I think you can't see the CO2. The CO2 is stuck below. So again, this diagram shows us what the effect of running at water-gas shift equilibrium is. If we want to increase the effect by putting in more water to change the water-gas shift reaction, we can increase production, as we pointed out before, by putting in more water, and then notice the water-gas shift line goes over there. So in a gasifier where mostly water-gas shift is close to equilibrium, the gasifier will follow one of those lines, depending on the temperature at which we run the gasifier. What about deposition of carbon? Deposition of carbon is the reverse reaction. We don't want to deposit carbon. If we run at 700 degrees Kelvin, we can write this on this diagram. That's where the deposition of carbon would be, above that line. Which means that we only got that tiny little region to operate at 700 K. However, if we go up to 1200 K, our water-gas shift equilibrium line goes there. And suddenly this whole region becomes possible. So now we can see the interrelationship between all of these factors on a very simple diagram. I mean, by the time you plot everything on this together, it does look a little like a spaghetti tree. But in principle, by bringing it up slowly, you can actually see what we're doing. So, I'm not going to tell you what we want to do. I'm merely telling you, here is a way of deciding what you can do. And once you've decided what you can do, you can readily look at it and say, what is it I want to do among those situations which are possible? I'm not sure what my security center update is doing. What do I cancel it?
Cancel.
Yeah, I also will be able to work it there. Right, so what we've got here then is a simple graphical technique which we can determine the possible operating regions for the gasifier. We can determine desirable operating regions and look at balancing the effects of desirable and undesirable reaction. And we can investigate the effect of gasifier operating parameters on gasifier operation. Now, what I guess if I'm to give a message from this at the end, what I guess I'm saying is, it is all very well to run simulations. But simulations don't tell you what you can achieve in principle, and it's only as good as your last guess. What I'm trying to do is get methods which allow you to assess what the conditions are under which you would like to do your simulation. So that's what the message we're doing, and we're using these graphical techniques in some of our Fischer-Tropsch work, which we're doing for building pilot plants in China and Australia. So these ideas, we believe, would make life a lot simpler for people to assess what to do. Thank you.
I think we have time to take a few questions.
I was wondering, when you run the simulations, so you figured out which gasifiers can actually, do you apply this as just a generic simulation for gasification, but which gasifiers can even operate in this range? And when you look at, you're saying if you increase the shift or increase the oxygen consumption, is that even technically feasible? Or certain gasifiers can, certain can, or whether there's a gasifier that can do any of that?
I think it goes the other way, because now it enables you to choose the gasifier you want that can achieve the conditions you want. So this is a tool pre-gasifier selection. And if there are a range of gasifiers available to me, then I can use this diagram to actually to decide which ones give me the best from a production point of view. Sure, there are all sorts of other technical operating conditions which haven't been looked at, but at least you can rank the gasifiers in the beginning in what they're able to achieve in principle. The techniques that we have available in chemical engineering tend to be simulation. We do not have techniques that step back first, take a step earlier and say to us, what is achievable and what can we do? We are trying to get the information that you need in order to go forward. And simulations are excellent and wonderful, but they don't answer a whole range of what I would call pre-simulation questions. And most of our work is associated with trying to answer those pre-simulation questions.
Right. Thank you very much. Thank you again.